Up till now, we've been talking about pulses. We are now going to talk about sinusoidal waves. These are going to be the easiest to mathematically analyze, and they're the most interesting ones that happen in nature. So if we want to talk about light, it's a sinusoidal wave. If we want to talk about sound, it's a sinusoidal wave. If we want to think about shaking a slinky up and down in a very regular way, that's also going to be a sinusoidal wave. So let's start by again returning to these three-dimensional plots that the book can show, but that as human beings who are not great artists, we can't really show. Note that if we just look at one time and look at different positions, you see a sine curve. And when we say sinusoidal, that just means shaped like a sine wave or a cosine, and you actually just have a different phase. We can also grab one position and look at different times. Now this is a little bit harder to see, but if I trace out where those points are, you actually are also getting a sine wave. It's harder to do it at any point that isn't the end. So you have sine waves if you go along position. You also have sine waves if you take a cut through this and look at time. So again, we're going to switch to looking at one of these dimensions at a time for the sake of being able to actually draw them. But you do have this very repeating pattern. When we have a history graph, that means that we're looking at one point in space, but we're looking at many different times. So D here represents displacement. Again, right now we're talking very generally. We're not talking about what type of wave we're looking at, which is why we call this D. So this is going to be displacement, where that could be electric field strength, that could be sound pressure, that could be light intensity, lots of different things, but we're going to keep it general. Amplitude is going to be A, and notice that we have positive A and negative A. Period T is the amount of time that it takes to go between two peaks. Now, based on how this works, we can actually grab this and, for instance, drag it. And notice that if I put it, for instance, between two troughs, you have the same time. I can put it between two intersections. This is a little more dangerous. So I would say in general, you want to be careful because you don't want to actually go from there to there. That is not a period. What you have to do is say, it's going up here. So I have to not look at that point because it's going down. I have to go here where it's also going up. So it's valid to use this as the period, but I would encourage you to use peak to peak or trough to trough. We also call these crests, whichever terminology you want to use, but be careful about using intersection points because it's not this one in the middle. You have to have an up and a down for this to be period. So again, we call this period, and that tells you about the repetition. That is true when you have time on the horizontal axis. So remember, history is one point in space. You see a window in time. That tells you about period, and we can go from period to frequency since period is equal to 1 over frequency. This was something that we met when we talked about pendula, and it's still going to be true here. So that equation is still true. Period is what you can read off the plot. Frequency is what we actually talk about more often. So if we have a snapshot graph, that's looking at our position. So we have one instant in time, but now we have position on the x-axis. Notice that displacement is still what's on the vertical axis, and nothing has changed about our amplitude. Now, when we again look at the repetition, we're going to call this wavelength. So notice that it looks sinusoidal in both time and space. So be careful when you go to read off a value to know whether you're reading off period or whether you're reading off wavelength. Again, I'm going to typically call these peaks. The book calls them crests. That doesn't really matter. And again, wavelength will also work if you go from one intersection point, in this case heading down, not this one, but to the next intersection point where it's also heading down. So this value is also going to be wavelength, and we use the Greek letter lambda for that. Now, if that letter looks familiar, it's because we also use that for linear charge density. There's just not that many letters. A lot of them are getting reused. So again, be careful when you turn to the equation sheet. The equations on the equation sheet are organized by what section they appear in, but also make sure that you vaguely know what the equation relates to. You might be told something about lambda, and that could be wavelength in one problem, or it could be linear charge density in another. So a few notes. When we talk about amplitude, that is 0 or equilibrium to maximum. So if I go back and show you what I mean, amplitude is going to be from this 0 position up to A. Notice that it's symmetric, so you could also think of that as 0 down to A. But it's not from top to bottom. Top to bottom is actually going to be twice the amplitude. So that's something that can be a little unclear. So if you're told that from max to min is, for instance, 2 volts, your amplitude for the definition we're using in this class is then 1 volt. So please be careful about that. That's important to distinguish. Second is to notice the difference between period and wavelength. They are both peak to peak, or crest to crest, trough to trough, however you want to talk about it, but period corresponds with time, wavelength corresponds to space. And this is just something that I see students not pay attention to. So be careful about this, pay attention to the details, they're really important. And then lastly, period is what you read off, but we'll talk about frequency a lot, and that's just 1 over period. So in symbols, we usually use the curly F for frequency, and then period was again capital T. So that equation should look familiar, and we'll be using it now.